Okay, good afternoon, everyone. So today we're going to start off by talking about generalized additive models. And this is somewhat of a continuation of what we were talking about last class with splines. And so to kind of reiterate some of the pros and cons of these spline-based approaches versus the more sort of traditional like linear regressions, right, is that you're able to, like I was saying, you're able to do a lot of much more high-powered prediction, especially for functional forms that are not linear, which tend to be the case when you are thinking about real-world data. But there are some benefits of having these like nice interpretable beta coefficients, and so general additive models are a kind of nice hybrid between the two that let you retain some of the functionality and power for each of those respective models. So this is actually one of my favorite approaches for doing different sorts of data analysis because it maintains some interpretability by additivity of terms. And so the basic idea here is that I can actually choose to use a spline function for individual variables, and then you kind of add them together. So the whole idea would be, if I have yi equals beta 0 plus beta 1 xi1 plus beta 2 xi2, and so on and so forth. Well, then here I can additively create these sort of splines for individual variables. And so this is my smoothing function. And the beauty of this is you can look at kind of the shapes of the spline in individual variables, and actually if you see any ones that are just lines, you could just revert back to having, if like x1 looked linear, you could just leave that as a linear part of your additive model, since each of the variables are independent. Okay, and so I think the sort of really best value in seeing how this works is just using a sort of applied example. So let me just go ahead and jump on over to R. All right. Okay, so we're going to use the ISLR library again so that we can use our hitters data set. And then the other package that we need is MGCV. So I'll go ahead and run these. MGCV stands for Mixed General Additive Model Computation Vehicle. It's just the nice sort of library that folks use to do these GAMs, these general additive models. So let's take a look at this. And actually, before we do that, we can refresh our memories about this hitters data set again. So it is a baseball data set of a bunch of individual player statistics, at bat, hits, home runs, runs, and so on and so forth. And so what we're going to predict is their salary as a function of a bunch of these individual player statistics. So normally you would have something like this plus hits, for example. And what I'm actually going to do, so instead of in the LM, you can actually have put an S here, and the S stands for smoothing spline. So it's going to have this internal spline function applied to any variables that you would like it to be applied to. So let me, there's a few variables here, so I'm just going to go ahead and copy and paste it. So we're going to look at bat, hits, walks, C runs, C RBI, C walks. The division that they're in is a dummy variable or categorical variable, so you can't actually fit like a spline to that, so we just leave that as is, and then put outs. So I'll go ahead and run this model. And you can see this summary here. And these give some significance terms for the smoothing values. And then for any terms that you chose not to apply a spline smoother to, you can get the actual linear estimates for the coefficients, right? Just as you would in a normal linear regression. So I think one of the really nice features about this is that I can look at the shape of the spline as it pertains to each individual variable with respect to my outcome. And I think that's where you get a lot of value in being able to see the sort of individual type response. And because you are making an additive model, it makes it so that you don't need to view the contribution of your X variable in like multiple dimensions, or it's not kind of like combined with other variables like in a principal components analysis. And in that way, you can't necessarily say anything interpretable about like a slope, but you can look at the shape of it. So let me just plot this so we can see kind of what I'm talking about here. Okay, so this is a plot of each of the GAM fits. So let's take a look at an individual one and kind of break down what's happening. So our response variable is salary, and so that's what you're going to see on each of the y-axes. And for the at-bat, we can see kind of the shape of this curve. And it's actually, I would argue, relatively flat. So you're not seeing a huge amount of difference in a person's salary based on how many times they sort of go up to bat. You'll notice that you've got these error lines around your spline function, and they tend to get a lot larger when you have sort of place areas with less data. And so these lines at the bottom indicate the actual observed points. And so that is important for example, like over on this C runs chart, you'll notice that most of the points, oh yeah, C stands, I think C is career. Yeah, so for your career runs, most of the players are going to be between 0 and 500. And as you go farther and farther out, you see kind of larger errors because it's calibrating to less data points. As opposed to like something with walks, it's actually fairly uniform across. And so this GAM model allows you to look at the individual effect of the variable on your outcome, and it lets you oftentimes see how they're like non-linearly related, right? And so for hits, for example, you can see how there's this kind of a little bit of this wavy curvature as you go up for hits. For walks, it seems to be, it's a fairly sort of not a very large effect or a zero effect up to a certain point, and then it starts to increase. So you have this kind of like kink type of thing. For career RBIs, right, you have kind of an increasing slope at the beginning and it kind of levels off later. And then for career walks, also you have this kind of interesting effect here. Obviously fairly nonlinear. So this is a nice kind of compromise between being able to incorporate some of the like flexibility in the functional form of the relationship between your variable and between your explanatory variable and your response variable, while still maintaining some interpretability in what an individual variable's response would be against the explanatory variable. Other kind of things to note is that oftentimes we are kind of modeling some of these as lines, right, within a linear regression. And so I typically always encourage folks that even if you do want to just do a linear regression, maybe you ought to do a fit with splines first so that we can see, okay, if I assume, that putouts is linear, that might be a pretty reasonable assumption. And in fact, kind of looking at this, I could just change this to be a linear variable as we sort of traditionally think of it, and I would have removed the splines. But maybe that wouldn't make a lot of sense to do it for career walks, right? Because it's definitely not aligned. So this is also a nice like diagnostic tool to see how your assumption of linearity kind of holds up for any individual variable. So you could always like run this with the GAM first and then do a linear run later to see. And so if I were to run this model, right, it's kind of the same thing, except now the like putouts part is entirely linear in kind of the same way that our traditional linear regression models would kind of describe it as. Yeah, and so I think the general additive model is really a nice kind of hybrid tool that allows you to leverage some of the predictive power and flexibility of form with some of the stuff that we were talking about in the last lecture while still letting you interpret variable effects individually, even though it's kind of a little bit less straightforward to do than just stating a beta. Okay. Any questions about that?
Could you please like give us an example of how to interpret like one of the coefficients?
Yeah, so okay, so again, so these ones you don't have a coefficient anymore. Okay, so these coefficients are just like the linear one, right? I would just say for every additional put out that the player has, their salary will increase by you know, 0.2 or 0.19. But here, the way that I would interpret this is that, oh, you know, if I go from 60 walks up to 80 walks, my salary will increase from, you know, this point to this point. So the version, so if these were all, you can think of these as representing it's a function that describes the relationship as opposed to just the beta. For the beta, it would just be a line, and then we would say the slope is that relationship. But here you no longer have betas, you just have this line to describe the relationship. So it's harder to interpret that directly, but you could always just provide the plot and kind of describe them individually. Hopefully that makes sense.
And also, Professor, like in the output below, what does those values mean? Like EDF, is that like estimated degrees of freedom or something?
Yeah, so these are diagnostic terms for each of your variables. EDF it's not estimated, it's effective degrees of freedom. And you can use these to essentially see whether or not the model thinks the effect is statistically different from 0. So it's kind of like what you would be doing with the beta, but it's not, the way that they do this is a little bit less straightforward. But you can think of it, yeah, as you can interpret these significance kind of in the same way that you're interpreting the significance for your beta coefficients. It's basically the statistical hypothesis is that your effect is non-zero essentially. So that's what you're testing here. Okay. So that covers yeah, that covers the general additive models. So splines and everything that we've done sort of building up to splines and then the general additive model itself are examples of kind of semi-parametric models wherein the functional form is flexible and within the model can be essentially endogenously changed. There are sort of the sort of next level is to think about entirely non-parametric approaches which don't use any assumptions about functional form, about any particular parameters. Just it's not trying to calibrate any parameters for the model. And so this is also kind of a nice approach that lets us have highly flexible fits to the data. And once we get into this territory, again, we are sort of definitely more in the bounds of looking at predictive measurement rather than doing any inference. So the classic example of this is kernel regression. Okay, and so let's go ahead and get the mathematical definition out of the way, and then I'll sort of show a graphical sort of concept of what's going on. So we have our y hat x is equal to some I with this k function of xi minus x divided by h times yi divided by the sum of I of xi minus x divided by h. Okay, so we'll actually get back to this equation in a second, but I'm kind of putting this out first as reference. So here is the concept. Let's draw some points here. Okay, so let's go here. And we'll say at this x, what is y? So you're essentially predicting a particular outcome based on distance to nearest points. And so you can actually think of this as, in theory, similar to the KNN model. But if you remember, the KNN was for classification, whereas this one, we're actually trying to do predict a continuous outcome. So it's gonna, in some way, kind of look to its neighbors to decide where it should be located. So kernel is based on weights. If we weight points more heavily, if they are close, then you would maybe have something that looks like this, where I'm going to choose this point here because those are close. And these ones will have not much of an effect. Whereas if weights for farther points are considered, then our plot might look a little bit different. So if I draw the same kind of 5 points, and we want to look here, then maybe it ends up being slightly higher because it is now being influenced by kind of all 5 points. So you can see how the red dot has, in this case, kind of moved up a little bit. And again, the idea is basically thinking about which kind of points influence the position of my prediction. Okay, so let me just bring this back up here. Okay, so in this kernel regression, H is the bandwidth. The larger it is, the more we consider farther points. And then the smaller it is, the more we consider local points. So you can, if you look at this equation, right, we can see that H normalizes xi minus x when big, right? Because you're dividing by a large number, and therefore xi minus x is getting normalized across its range of values. H magnifies xi minus x when small. So like if H is less than 0, it'll, or it's not less than 0. When H is less than 1, it will start to increase the difference of xi minus x. So there are a couple different examples of this kx function, which is the which is essentially the kernel function. And I'll just give a couple of the most common examples. So you've got the box kernel, and this is k of x is equal to 1/2 if the absolute value of x is less than 1 and 0 otherwise. So what ends up happening, right, is that if your xi minus x divided by h, if your h is really large, then it will count. Let's say it counts all the points because then this just becomes 1/2 times your yi. If your h is really small, then it's only going to consider the closer points, because the difference is going to be really large, right? Your xi minus x numerator will be really large. It's going to be getting divided by h, a small value, which becomes really big, and therefore your kernel is going to get counted as a 0. So the farther points will have no influence, but the close points will have more influence. So that is how a box kernel works, and the principle of these kernels is going to be essentially very similar. So a different type is a Gaussian kernel, and this is where your k of x is equal to 1/√2 pi exp of negative x squared divided by 2. So the way this kind of works is that you have a sort of normal distribution, and kind of based on your distance, the weights are going to be essentially like shaped like a Gaussian distribution. And then probably one of the most common ones, actually, let me make sure I'm spelling this right. A Paneshnikov kernel. And so this is kind of similar to the box kernel. I don't know why this is one of the more common ones, but it looks something like this. So 3/4 1 minus x squared if x, absolute value of x is less than or equal to 1 and 0 otherwise. Okay. So that's kind of some of the kernel functions that are commonly used in this type of regression. So let's go ahead and take a look. Let's take a look at how this works in R. Okay. So what we'll do is we are going to grab the same point generation that we're looking at for our semi-parametric models for the splines. And that looks something like this. And what we're going to do is use the NP library. Okay. So NP stands for non-parametric. and we are going to use kernel models. So one thing that you have to do for the kernel is to order your values. So this will just go from smallest x to largest x. So we'll go ahead and do that. And that'll be this, well, sorry, this actually isn't for the model fitting. This is for the prediction later and drawing out the results. Okay, so our kernel model fit will be using the np-reg function, non-parametric regression, and we'll be regressing y on x. And the only parameter that I have is for my h, also known as the bandwidth. So I'm just going to put kind of arbitrary bandwidth for now, and we'll see kind of what happens. Oop, I need to load this. Okay. So we can look at the summary of this, I believe, but it's not really going to tell you anything. It's going to tell you a residual standard error, an R squared. It's going to tell you that the kernel function that we use is a second order Gaussian. And here you can actually change the kernel type. If I do here, let's see, so. Okay, I thought that I could. All right, I'm not gonna, oh, here we go. No, that's the plotting errors. Okay, never mind. So I'll put it in the notes. I don't remember off the top of my head how you change the kernel function type, but I guess the default that's being used is a second order Gaussian. So let's plot this.
Alan?
Yes.
I'm really sorry. Could you just show us the y function again? I missed that.
The y function?
Yeah, like the y is equal to sine x something?
Oh, right here. Yep.
Oh, thank you.
Here.
Thanks.
Yep. It's the same one as from our previous lecture. And actually, I'm actually gonna grab it here and plot it. Okay. So what I'll do is plot the actual function so you can see it here. So this red line is the known true function on which we were using to generate these points. So our kind of objective is to make a fit line that matches the red line as closely as possible. So I'll say, I've selected, I would characterize probably a fairly small bandwidth. And so if you guys recall, well, okay, actually, no, so let's, I'm jumping the gun here. Let's just take a look at what this is. Okay, so if I plot with the blue line, you can see the fit seems to be doing a fairly good job. It's pretty close to the red line, right? You might be off it in some places, but otherwise it's doing a fairly good job. And again, the way this works, right, is it says, okay, if I want to predict an X like right here, I'm going to look at the X's, the value of the Y's for X's that are really close to me. And I'm going to weight them. I'm going to give them some weight. They're the ones that are closer are going to be sort of more important, and the ones that are farther and farther will be less important. So let's see what happens to this line as we change the bandwidth, that H value. So I'm going to do kernel model 2, and why don't we make it smaller this time? So again, if you remember, as the bandwidth decreases, we start to consider local points more heavily than farther away points. So I'm just going to change that to 2. So let's run this. Okay, so once we, as we decrease the size of the kernel, it will again place more and more emphasis on the local points, and now we'll start to get some of these little squiggly lines you can see, particularly in the middle here, when it's changing, especially when it's changing directions, you'll start to see more and more, or as you can see, some kind of spikiness happening here. And we can continue this trend and see what happens. Let's say I'll change it to 0.01 instead of 0.01, or 0.001 instead of 0.01. Kernel Model 3, and you can see, okay, you start to see this jumping back and forth as it essentially will start to favor individual points to a much larger extent. And so at any particular one, it's going to snap to kind of the nearest X, right? And so you see this effect happening where it jumps up and down a lot. And here we are very clearly jumping to the classical issue of overfitting. And this gets back, this hopefully will point you guys to start thinking about, okay, how is it that I choose the right value for my bandwidth? Same thing, same way that we've been doing before. It's going to be some form of cross-validation. Let's take a look at what happens if we go the other direction. So let's do model 4, and let's go, I think the first one is 0.05, so let's double that. We are now increasing the bandwidth, which means it's going to start valuing, farther and farther points more when it decides to do this kind of weighting. Okay, and so you can start to see some diminishing of the line as it's averaging out points that are farther away. Let's change this to, say, 1. Let's see what happens. Okay, so then again, sort of doing these longer averages. And lastly, let's try the most extreme, 10. And then it's, or I guess, what do you guys think is this value? Like, what is this value here, this straight line here?
Just the average Y value of all data points.
Yep, exactly. So it just takes everything into account. And when you think about the KNN model, where it says which one's the most prevalent, it's basically the same sort of principle here, where I average all of the values, and then it's just flat across the whole solution space. Okay, and so I think one of the, we can see from our first one, and we'll get actually a better example of this in a second, that we're actually able to do a really nice job of fitting to this prediction, and the spline was able to do that as well, right? But they're doing it in very, very different ways, right? The spline is this semi-parametric approach that has this kind of functional semi-functional form of doing these cubic splines with the with the smoothing spline. It would have a number of knots equal to the number of points, right? It's a very, very sort of different approach, but you are getting to similar outcomes in terms of prediction. Very quickly, let's just show. So I just copied and pasted some code to do cross validation manually. It'll be in the notes online, so you'll be able to see this. I'm not going to go through it, but it's basically the same thing that we've been doing before for k-fold validation. And what I can do is run the kernel model through a range of different bandwidths and look at the out of sample mean squared error. And so if I go ahead and run that, we can see what the results are. It's going to take a little bit of time. Okay, and so I can look through all of my mean squared errors for every corresponding bandwidth. And the lowest ends up being about 0.025. So I have that sort of isolated here. And we can see when you run that, this ends up being sort of the closest to my red line. Okay. So why don't we take a quick 5-minute break here, and then we'll get back into it and discuss some of the differences between the splines and kernels. I'm happy to take any questions in the meantime.
Professor, can you please scroll all the way up? I have a question about the generalized additive models.
Yeah.
Cool. So in line 10, is there a way, like, let's say I have hundreds of independent variables. Is there a way to apply the S function to all of them at once?
Yeah. So you could do it, let me see. Yeah, I don't know if there's an automatic way. It might be something like this. So, okay, so applying spline function to multiple variables. It might be something like this. I'm not sure. You could check it. So y on s dot. And that would be doing it for kind of like the way that you had were equivalent to y dot like that in LM, but I'm actually not sure if that works. If I had to guess, that's one way that you might be able to do it. But the other way that you could do it is to paste it in as a formula. And so if x is a vector like x1, x2, x3, x4, etc., then you could kind of do it like you would do it in the homework. You could paste them together, paste x, and then you would collapse equal to, let's see.
Plus S, I guess.
Like that. And then you would want to wrap that in, wrap the above in paste. So let's say this is like hold, wrap the above like this. S hold to get the last pieces. And then you could put that into a formula, and then put that into your model fit. So similar to what we were doing in some of the notes and in the homeworks. So this would be yeah, I would do something like this.
Cool, thank you.
Yep. Okay, so let me finish up with talking about when you might want to use splines versus kernels. So splines versus kernels. So computational speed is going to be quite a bit faster for splines, especially when you're talking about larger and larger data sets, right? That functional fit compared to with a kernel, I have to mathematically calculate the weights for every individual point to do my prediction. Simplicity. And I guess what I mean by that is that with the spline, you are talking about some kind of interpretable relationship between your explanatory variables and your response variable, as opposed to kernels. It's all has to do with kind of like the individual point in space relative to all the other x's. So there isn't really anything about interpretation, especially once you're talking about going into multiple dimensions. So clarity of controlling curve directly. So there are like different ways that you can affect the spline itself, right? Either by what kind of spline you're using, you know, the placement of the knots. These can all influence the curve in ways that are kind of customizable for that particular fit. Whereas in the kernel, you don't really have that ability, right? Because everything has to do with the individual points. But in a kernel, it's, I would say, easier to program, especially to extend to multiple variables, right? So in a kernel, that doesn't really matter. I could just add in a bunch of x's, and now it's just doing distances in multi-dimensional space. Whereas with splines, doing combinations of these variables can be very difficult, and a lot less straightforward to do. Easier to analyze mathematically. Right, because I can look at an individual point, I can plug it into my kernel equation, kernel regression equation, and calculate a prediction. And combinations of discrete / continuous variables is easier. Okay. Any questions as we kind of wrap up this discussion about semi-parametric and non-parametric models for regression purposes?
Oh, could you explain again what the role k plays? Like, and it's a function of x, not xi minus x.
Yeah, sorry. Say that again. The role of what?
For in the kernel functions, like k in the equation, like the.
Yes. Yeah. Let me jump to the whiteboard. Yeah, unfortunately, all that stuff disappeared, huh? Okay, so you're talking about this big K here?
Yeah.
Yeah.
Oh, is it? It is a function of x minus or it's a function of everything in the parentheses.
Yeah, exactly. So you have like K of x. Let's just do, yeah, let's just do a quick example. If x is less than or equal to 1, 0 otherwise. Let's say we have 2 points. We have x, y, we have x1 at 1, 1, and we have x2 at 2, 2. And let's predict for x equals, let's say 0.75. Or no, let's say 1.75. And then let's do our bandwidth is equal to, let's just say, let's say 0.5. So to predict for this particular point, it would be so you have sum of I, so this would be 1, 2, because we have 2 points. So for I equals 1, k x1 is 1 minus, we want 1.75 divided by 0.5. And this is equal to, so 1 minus 1.75 is 0.75 divided by 0.5. That is less than 1, right? Half of 0.75 is less than 1. And so therefore this is 1/2. And for I equals 2, okay, and so then it's 1/2 times my y1, which is 1. For I equals 2, it's k times 1 minus, 2 minus 1.75 divided by 0.5. Okay, that's still less than 1, right? And since we're using the box kernel, then it should be 1/2. So it's still 1/2 times 2, and then you add that up, and then you use the actual values down here and divide it, and then you'll predict some value of y. Does that make sense?
Yeah, that makes sense.
Yeah, so this is just describing this kernel function here. Okay. So, everything that we've talked about in class up to this point has been a form of what we would call supervised learning. And what supervised learning is essentially models that have an explanatory variable, or sorry, not opposite, a response variable whenever you have a y. And so everything that we've done has been looking at various ways of relating some explanatory variables to a particular outcome. There is another whole class of models that are used for what is known as unsupervised learning. So this examines undetected patterns in data. Focuses on settings with only explanatory variables. there are no response variables. So you are not interested in prediction. Really, you want to identify subgroups among variables. And you're unable to conduct validation, right? Because you have nothing to validate on. You're not looking at any particular outcomes. And because of that, you have no like training set and testing set for to calibrate any of your models. I would say the two common applications principal components analysis. And this is actually kind of the backbone of what we talked about before with principal components regression. But instead of looking at any relation to an explanatory variable, a lot of this is going to be for like data visualization or pre-processing of data. And the one that I think most people have worked with or have heard of is for doing clustering or cluster analysis. So we'll talk about some examples of clustering algorithms today. Probably the most famous, most used, or maybe more, I would say, most common clustering algorithm is known as the k-means clustering algorithm. And the whole idea, this is a simple approach to partition data set into k distinct non-overlapping clusters. One of the features about the k-means clustering is that k must be pre-specified. And we can talk a little bit about some ways in which people decide what k to use in a bit. So I will show, okay, I'll show the mathematical notation really quickly, and then we'll talk about what this algorithm is actually doing. So minimize C1 to CK. So this refers to number of observations in kth cluster times the sum of I, comma, I prime elements of CK times the sum of J1 to P of Xij minus Xi prime J squared. Okay, and this is, I think, another one of those instances of like the equation is I think maybe a little bit more complex than or I think the algorithm itself is actually fairly straightforward. So let's talk about that and see how this works. So step one, randomly assign 1 minus k to each observation. Iterate until no more changes. In step A, for each k cluster, compute centroid. And then step B, assign each observation to cluster with closest centroid. Oh. Euclidean distance. So note that scaling / normalization can be very important here. Okay, so that's it. The algorithm itself is actually quite simple. Let me maybe draw an example of this. So let's say I have a couple points. Let's say we've assigned these points to 1s and 2s. 2, 2, 2, 2, 1, 1. Let's say I figure out that the centroid of my 1s based on Euclidean distance is over here, and that the centroid of my 2s is over here, just based off of the Euclidean distances. Then my next step would be to reassign each of the points. So which ones are closest? So my 1, 1, 1, and let's say this becomes a 1, and then the other ones 2, 2, 2. These all become 2s. And the new centroids based off of the Euclidean distances might look something like this and like this. So that's x1, x2. Okay, and then you repeat this process where I reassign points closest, but if it looks the same, So if the plot ends up looking the same, which it will in this particular case, then we stop and we say, okay, these are the assignments, right? And this is for k equals 2 in this case. So it's actually a fairly straightforward procedure, right? You are basically calculating the centroid, assigning the points. You start by first randomly assigning, calculate the centroid, they'll start to move, and then at a certain point it converges until you have a point in time where the points are no longer getting reassigned, and then that's kind of your final clustering. Okay. So let's jump over to R. We should have an example of this. Okay, any questions about this? I think we've already loaded ISLR. Yeah, we have. Okay, so we don't need this. And we're gonna load up a data set called auto. And we can take a look at this. And what we're gonna do is to look at a clustering of points in the auto data set. And so here are some vehicle attributes. And what I'm going to look at is cluster of MPG and horsepower. So let's plot that first just to see. Okay, so we have all of these points here. Okay, as I mentioned, the first thing that I'm going to do is to normalize the points, because you'll notice that horsepower ranges from 50 to 200, MPG ranges from 10 to 40 or 10 to 50, and I want those distance weights to be sort of equally distributed between my axes. You don't always need to do this. It depends on the context of your particular problem. Just don't forget that the clustering is going to happen based off of these Euclidean distances. So if you want them to be sort of equally weighted between your dimensions, you need to do scaling. So the way this works, it'll be MPG, like that. And so when I do this, if I look at auto.scaled, it's going to return scaled values for these two variables. And what we can do is do our k-means model. And here I'm specifying explicitly having two clusters. And you can change that up to an arbitrary number of clusters that you want. And I will actually just add that into, okay, so we'll run all of these guys here. We can see what that looks like. And it tells you the centroid locations of my two clusters, so cluster 1 and cluster 2, the mean for MPG, the mean for horsepower, and then it tells you essentially like each row, right, which cluster assignment it's given to. and then within cluster sum of squares, and then there are a couple other metrics that are stored within this model. So we'll take a look at what this looks like. I'll just actually copy and paste this to save a little bit of time. So basically what I'm doing here is I'm assigning back into the original data the cluster assignments for the models where it's run from clusters 2 up to 5 clusters. So if I run this, we can go into the original data set here, and for every particular car, I can see which cluster it belongs to depending on how many clusters that we have created. Okay, and you can plot this out explicitly like such. Okay, so if you've only got 2 clusters, you'll notice the points will end up getting clustered like so. This is based off the original points. They're not the way the plotting is. They're not scaled, but because the distances on the axes are spread out kind of evenly, the visual version here is actually a nice kind of representation of what it's going to look like if it were scaled anyways, because the kind of horizontal distance and the vertical distance are about the same. So it's reflecting the spread of points. So this is for 2. This is for 3, for 4, and for 5. You don't always have like an equal number of points in each cluster. And hopefully you can see that here, like in the red, there are definitely far fewer points in this red cluster than there are in, like the green, or I guess any of the rest of the clusters, which actually look maybe somewhat a little bit more even. Yeah, and that is just an artifact of however the algorithm sort of turns out the assignments of clusters. Okay. So that is k-means clustering. Some of my experiences with k-means, it's very reliable, it's pretty fast, you can do it on pretty large data sets. One area where you might get into trouble is thinking about the application of clustering to, and I see this all the time actually, discrete points. So obviously this is all based off of like average distances. So you can't actually apply this to, like factor variables, like dummy or categorical variables. Because, there isn't really a meaning to distances between categories or, factor variables. That's entirely arbitrary. Where you'll see a little bit of controversy in this area is the application to things like Likert scales. So this is particularly prevalent in survey data where you have something like, so generally it's this kind of question like, how much do you like X? And it might be like a 5-point scale where it's something like a lot, a little, you know, and like something like this. And then they get coded as 1, 2, or oops, as 1, 2, 3, 4, 5. And some people will argue that the like qualitative difference between each of these is kind of equally spaced, and so you are allowed to apply clustering algorithms such as k-means that depend on distance, and you'll find some differences of opinion, I would say, in applying this type of approach to that kind of data. All right. Any other questions about k-means clustering?
I have 2 questions actually.
Yep.
If you can scroll back up in your code a little bit when you created the auto scale, that line of code does not run through me. The period especially seems to be problematic.
Yeah, so I think you need data table for that to work. And you have to make it a data table. I think if it's not a data table, let me see, is the scale a base function? It is. So if you aren't using data table, then use the following. You should be able to do this. You're just scaling the columns of your data frame. The period is for data tables as a replacement of typing list, which is their way of not doing this C thing. But yeah, so this would work in the base package.
Okay, I think what I just forgot to actually run the code that made auto a data table. So
this one here.
Yeah, I had it typed in. I just must not have run it.
Yep.
And then my second question is, since we have to pre-specify k.
Oh yes. Right. You're asking, are you going to ask how you should pick k?
Exactly.
Yeah. Okay. Yeah, so that's definitely a little bit more it's not, there's no kind of like preset way to select k. You know, you can make an argument for however many clusters based off of the context of the problem or need that you're trying to do. The quantitative way that people have thought about trying to do that is, let's see, if I do k-means dot 2, you can look at, oh geez, I think it's the total SS. One second, let me just double check to make sure. It's the WSS within SS. It's called the elbow method. So the way that you do this is means dollar within. Oh, that's given here. Wait, I thought there's only one. It's yeah, okay. So what you do, so if you take the mean of the within sum of squared and then plot it as a function of your number of k's, so this is within SS, so this is the mean, mean of the within SS for k equals 1, k equals 2, k equals 3, and so on. The graphs will tend to look like this, and the way the the way that people choose the k is they you look at where I guess the slope changes the most, and you pick the number of clusters where that happens. And the way people describe it is the elbow method, where you pretend like it's an arm and the number of clusters is like the elbow, essentially. Yeah, and I think that's one of the most common ways that people select their k. If they don't have some kind of predetermination for a number of clusters, and it's kind of open, then they choose using this kind of method. And it's not going to be always that clear when you do this. It is possible that that the kinks will be it's not going to go up, but that you know the elbow might be very very kind of bendy, I guess.
So when you say where the slope changes the most, that's compared to just, sorry, so on what figures, and some of the points look especially steep, but we're mainly just looking for like where the biggest change happens.
Yeah, where I guess where it starts to flatten out and the slope stops changing very much, I guess is the way I would describe it.
Okay, so even if we did like say k equal to 4 was just barely lower, but it was very close to k is equal to 3, we would still choose k equal to 3?
Yeah.
Okay. So basically we're trying to catch it when it's flattening out, but do we want to keep k lower in general?
No. I mean, k is really actually pretty arbitrary for what value you choose for it. Yeah. Again, kind of going back to the concept that like in unsupervised learning, you don't have anything to do any kind of validation on, because it's kind of just you're just looking at grouping points essentially, and it's not as though the clustering themselves have any like predetermined clusters that you can check against. Otherwise, that would just be a like response variable, and so there's definitely some kind of qualitative aspect to like selecting the number of clusters. And we're going to do, I Yeah, I'll probably put it off to next lecture, but like for hierarchical clustering, which is the next clustering algorithm that we'll talk about, it's the same thing where it builds this like big tree, but then you essentially are choosing where to like chop your branches, which is going to determine how many clusters that you have. And that part, again, is like externally specified. It doesn't really have to do with anything about the like data and model itself. And this whole thing about the elbow method is like an attempt to try and have some kind of like quantitative justification for choosing the K, but really it's still pretty arbitrary, I would say.
Okay, so it would depend kind of on your objective in using this. Like if you were
Yeah, exactly.
trying to have fewer groups, then you would probably choose like K3, even if K4 and 5 were close. But then if you were just trying to find the best,
yeah,
then it
because
could be hard.
yeah, because the like qualitative or quantitative justification for the elbow method is not really that rigorous, right? It's just talking about looking at differences of the mean within sum of squares, but it doesn't really mean anything.
Okay, thank you.
Okay, and I see another question. Can we employ K clustering using more? Yeah, more than 2 variables. Yeah, you can use an infinite number of variable. Well, not a literal infinite number of variables, but yes, any number of variables can be put into your k-means cluster. And in fact, I did not test this out, but whatever, we can do it. Let me look at auto. So let's do weight. Let's group weight as well. So now it's factoring in centroids for weights. I don't know what the best way to plot this is. Actually, let's see. That would take too long. Okay, but you can see that like it works, right? Like I can very easily cluster on more than 2 or more than three variables. You can do that as much as you want, and then it'll do the assignment, and then you'll have to figure out some way of visualizing that if that's what you want to do. But it's not a problem to do k-means clustering for more than 2 variables. Okay. Any other questions? We don't have enough time to go through hierarchical clustering, so I'm going to push that back to Wednesday. And we will talk about yeah, we'll go there, and then we'll start getting into some other approaches that are used in machine learning, going back to supervised learning. And then homeworks will be due Wednesday at the end of the day. Yeah, and so if there are no further questions, then I will see all of you guys on Wednesday afternoon, and I'll stick around a couple minutes just to take any questions if anyone has any.